welcome to Module 19 on feature maps and the kernel trick. Here I'm just importing some libraries that I'm going to need today. We're going to do a lot of sklearn and a little bit of plotting. As always, we have a standard random seed so that we can reproduce our results exactly. By the end of this module, you should be able to explain what a feature map is and how it induces a kernel function. You'll be able to define and recognize valid kernel functions like linear, polynomial, and RBF. You'll be able to derive at a very high level, very high, how a regularized linear model can be rewritten purely in terms of kernel evaluations. You'll be able to implement and compare linear and kernelized models. Some of these will actually be in a future module. We've moved things around a little bit. And finally, you'll be able to analyze and justify kernel parameter choices, such as C and gamma. At least gamma we'll see today. C might be pushed off to another module. So let's again scaffold our concepts. So think of a two-dimensional classification problem. So just points in a two-dimensional space, but you have these half-moon clusters. You're going to see these in a moment, but these are sort of like two C's, two letter C's eating each other, like two interleaving crescents. You're not going to be able to draw a single linear classifier, either with a logistic regression or a linear SVM. These classifiers can only really draw straight lines, or at least pretty sharp gradients, linearly through this space. And this generalizes beyond 2 dimensions to higher dimensions through higher order hyperplanes. So the data are going to be curved, and therefore we want the classifier to be able to have curved decision boundaries. So the first option is to hand engineer smarter features. So x1 squared, x1 times x2 kind of gets some nonlinearities that way. So if we have some nonlinearities in the feature space, then hopefully those will somehow induce a linear decision boundary. We'll come back to this option in a future module also. We could try jumping to a more complex model family like deep networks, which we've at this point might only vaguely understand, to have like more representative capabilities. And not to sound like a broken record, we'll come back to this topic in a future module as well. But for right now, we're going to still use a linear model, but in a feature space that is richer than the one we're given by using something called a kernel. So we'll keep linear models in convex optimization. So all the topics we've been talking about before, we're still going to hold on to, very tightly. But we're going to secretly run the linear models in convex optimization in a much larger space. So here's the two moons diagram. Here's the code for it. I've already loaded this function before, make moons. This is a standard in sklearn. So you can see these are the two classes down here in the original input space. There's 2 dimensions. There's one class in purple, another class in yellow. And no matter how hard you try, there's no line you can draw through this space, which is going to really perfectly separate out these 2 classes. This is the original input space. And on the right, we have this 3-dimensional feature space where the features are not x1 and x2, but they're phi1, phi2, and phi3. Right now, we've invented like a nonlinear feature map called phi given the x1 and x2, the original feature space. This will give us x1, x2, and x1 squared plus x2 squared divided by 2. So actually, phi1 and phi2 are equivalent to x1 and x2 respectively, but now we have this phi3, which is this nonlinear transform of the original features. And this third feature, phi3, is going to kind of lift the points in 3 dimensions. And you can kind of see that happening over here. So again, download the slides and play around with it yourself. You can kind of see the original feature space here top down. So here's x1 and x2. And again, it's really hard to break these apart. But now we move everything to the 3rd dimension, and we get this nice looking bowl shape. And it's still harder, but you can start to see how you might be able to rotate this graph around. I'm not going to get into it, but you can play around with it yourself so that it will be somewhat possible to draw a straight line through this space to separate out the 2 classes. So the core concept is this feature map that I just kind of jumped over. If fancy X is your input space. So you have D dimensions in real valued space. So x1, x2, all the way to xd. A feature map is this function phi, which maps fancy X onto fancy H. And H is, a possibly very high dimensional feature space. So at the very least, normally H has at least one more dimension than X did. So in the previous example, X had 2 dimensions and H had 3 dimensions. So a linear model in feature space might look like this. So we have our weights transposed, just like we had before with our regular feature models. Instead of passing a vector x, now we're passing this vector, which is phi applied to x. And again, this might raise the dimensionality. And then the bias term. And that's it. So we still have a model here, f of x, which looks like a linear function. The only difference is we're taking the input variables x and transforming them into a higher dimensional space. Especially using, we haven't mentioned that yet really, but ideally using nonlinear transforms, like polynomial features. So here we have, two-dimensional space x1, x2. We have the feature map function phi, which takes those two variables and then produces x1, x2, so no change. And then x1 squared is phi 3. Phi 4 is x sub 2 squared. And x sub 5 is x1 times x2, which is also a nonlinear transform. We also have random Fourier features. This is not detailed here. This is a little bit beyond the scope, at least right now, but we're going to see RBF kernels a little bit later on. RBF stands for radial basis function. So again, the key point right now, or a key point, is that phi of x might be much larger than x in terms of its dimensionality, which will give the model much more flexibility. And we can kind of define phi however we want. So we have a lot of flexibility to define these nonlinear functions however we might please. We can also do x cubed, x to the fourth, and so on. So that's a feature map. A feature map is just a transformation from one low-dimensional space to another higher dimensional space, possibly using nonlinear transforms. A kernel function, k, is a kind of a product of the feature space with the feature space, which gives a real-valued number. This is possible as long as there exists a feature map phi with this definition. So the kernel function of point x and point x prime, so 2 data points in the original space, x and x prime, is just this vector phi of x and phi of x prime, and this gives us the new space fancy h. So intuitively, the kernel function between these 2 points measures a kind of similarity between these 2 points, x and x prime. And the most common examples are probably these. The kernel function, which is just linear product. So it's the transpose of x times x prime, so the product of the 2 points. And again, these points are vectors, x sub 1, x sub 2, x sub 3, and so on. The polynomial function, so we know how to do this. So we have a polynomial of degree p. So it's just the product of the 2 points plus some constant c, all raised to the power of p. And now we have this radial basis function, sometimes called Gaussian function. Again, it's a kernel function of 2 points. It's a measure of similarity of 2 points to some extent. This isn't exactly the Gaussian function, but it resembles it somewhat. It's the exponential of minus gamma, where gamma is a hyperparameter. This is something we set ourselves, times like the 2 norm of these 2 points. So x minus x prime, the difference between them, and the Euclidean distance. Oh yeah, and gamma has to be greater than 0. We might come back to why this is in a few moments. So in this case, there's this this feature map function, phi, which kind of exists, but we don't have to actually define it. We're just defining the kernel functions. So linear, polynomial, and RBF Gaussian so far. This is by no means exhaustive. You can come up with your own kernel functions, but here we're just comparing 2 points and getting a single value out of it at the end. So given the training inputs, so you have x sub 1 all the way to x sub n, we want to define a kernel matrix, big K, which is in the space, the real valued space, n by n. So it's like a square matrix. These are all sort of the distances between points x sub I and x sub j. Specifically, the ith row and the jth column of this kernel matrix big K is just the kernel function between point x sub I and point x sub j. So many algorithms, SVM, like we're going to see soon, kernel ridge regression, Gaussian processes, kernel PCA. Again, we're going to see PCA a little bit later. These can be entirely written entirely in terms of these kernel matrices and kernel evaluations for at least a few points. You don't necessarily have to compute this entire kernel matrix. You can get by just, not always, but in some situations, computing just some of these kernel evaluations. And this is what makes the so-called kernel trick possible. Here's a little anti-example. I've kind of framed the kernel function as a similarity between 2 points. So is that kind of bidirectional? Is any similarity equivalent to a kernel? This, I mentioned it because this is a misconception that arises relatively frequently. If you decide just to make some similarity score between x and x prime, then you can use it as a kernel. And we want to just highlight that this is not always the case, because for many kernel-based algorithms to behave nicely and to be able to learn reasonable models and functions from them, the kernel must be something called positive semi-definite, or PSD. This might be a bit of an aside, so this is more of a kind of a warning for you as a real practitioner of machine learning as opposed to somebody in this class, but I thought it might be worthwhile to mention just because, just so this misconception might be avoided for you in the real world. So under PSD, for any finite set of points x sub I, the kernel matrix K must be a positive semi-definite. Arbitrary similarity measures, like negative edit distances, ad hoc scoring rules you might come up with yourself, like not all similarity measures are necessarily positive semi-definite. And then if you use non-positive semi-definite, kernel matrix, in quotes, this can lead to optimization problems that aren't convex. And like we've framed machine learning from the very beginning of this course, we kind of prefer optimization problems to be convex. And you might end up with numerical instability and strange behavior, especially if you're using some kind of iterative learning model. So kernel functions are similarity measures, but all similarity measures are not kernel functions. And that's just something to keep in mind when you go into the real world. We might even see some examples of this in future Jupyter notebooks. So digging a little bit deeper. Again, this is under the microscope, so this is sort of an aside, so don't worry about it too much from the point of view of exams and that sort of thing. But it's nevertheless still important to understand how machine learning works. So consider a regularized linear regression model in feature space. So we're trying to, here's our overall objective function. The left term here is the regular kind of squared loss between target y and the predicted points in the feature space, w times phi. So we've already applied the feature map, and we've moved the original data points x into some higher order dimensional space. We can still do the squared loss. So this first term is a squared loss, and then the second term over here, lambda times the 2 norm of w, is the L2 loss. So big phi, just the figure over here, this is the capital of this Greek letter over here, is the n by d matrix. We have n data points and we have big D dimensions. And the ith row is the feature transformation of data point I. That's all it is. The objective can be written this way. So you can rewrite this entire function over here as this term down here, 1 times the 2 norm of y minus big phi times w. This should be obvious. You can take the equation for the like the 2 norm from earlier in this course, and you can see how like this sum over here transforms into the 2 norm without any modification. Except to the we need this gradient function, this kernel matrix here. Therefore, given this, we can take the gradient of this function with respect to w and set it to 0, because we're trying to find these critical points like we saw earlier. So you take the gradient of this function with regards to w, set it to 0. So here's nabla of w, which means we're taking the gradient of this entire vectorized representation from the previous step. This is left as an exercise to you if you really want to get into it, but the gradient of this function with regards to w, you can kind of see how, well, this 2 is brought down. We take the gradient of what's inside of this little function. This gives us y times minus big phi w. The big phi also comes out, and we take the derivative of these terms with regards to w. This is really just like preliminary calculus. So, and we don't necessarily need it right now, but I'm just kind of walking through some steps just in case it's unfamiliar to you. The derivative of the second term with regards to w is just a constant times the norm of w squared. The squared comes down, and then we're left with w, and we're done. All of this being set to 0 means we're finding the critical point where the derivative is going to be 0. So this is where we get to a minimum of this function, which is kind of what we're looking for because we want to be able to set w, which is our parameters, in such a way that we are at the critical point. If we rearrange this function, because we want y to be on one side, or sorry, w to be on one side, we get these normal equations. This is also left as an exercise. This is nothing too fancy. We're just moving terms around, but nothing's really changing over here. I'm introducing the I over here. I is just sort of the equivalent of a 1 in matrix space here. So if you're confused about what this I is, this is just serving the purpose of a 1 in regular linear scalar space. So we're left with this. So this value of the w star is the setting of w, which gives us the gradient being equal to 0. So this is our critical, w star is our critical point. And if you look at all of this, this is essentially just the ordinary ridge regression that we saw previously. The only difference is we're dealing in feature space, not the original space of the data. So the so-called kernel trick via algebra, this is only a sketch. But this is how predictions can be written only in terms of kernels. So we have our kernel matrix, which we've defined. We have our training data. We define our kernel matrix, which is just kind of the pointwise similarities between points x and x prime. So we have that kind of stored in memory somewhere. In some sense, the kernel matrix becomes our model, and we want to make predictions using only this matrix of similarities. Can we even do that? So if we suppose w star, the setting of w, which satisfies this equation at the bottom. Suppose it lies in this span of training features. So we have big phi times alpha for some setting of alpha in real valued n-dimensional space. We can plug this right-hand side into the normal equations. So we can basically take big phi transpose times alpha and plug it in here where w star was, and here it is. We can do a little bit of fancy footwork. We can multiply both sides by big phi. Again, this is going to be left as an exercise to you, but you can try to make sure that I'm not doing anything I'm not making any mistakes. Sometimes it's going to be easy to see if you're left multiplying both sides by phi, then phi transpose y becomes phi times phi transpose times y. The left-hand side is a little bit more complicated because we have to kind of multiply through phi transpose alpha to both of these terms. But again, we'll do this as an exercise, and you'll see that nothing very complicated is happening. You'll remember also, I don't have to remind you of this, but just in case, there's a big difference between left multiplying and right multiplying if you're multiplying matrices as opposed to regular scalars. So left multiplication here is an important thing to remember. But if you're left multiplying both sides, the equation is still valid. So we've done this, but now phi times phi transpose is something we've already defined previously as our kernel matrix K. So K is just small phi, like the feature map of one data point transposed times the feature map of the other data point. This is by definition what we've defined as our kernel matrix. So that's interesting. So we can replace big phi times big phi transpose everywhere with just the kernel matrix. And then you can do simplification. Again, details omitted. I might want to have put the little pencil mark here because, like, for you taking notes in your journal, this is something for you to do. It's not really required for the course, but it's always good exercise to walk through some of these exercises. If you replace big phi times big phi transpose everywhere with k and shuffle things around a little bit, you should get this function at the bottom, the kernel matrix plus n, which is the kind of the dimension size, times lambda, which is our hyperparameter, times I, the identity matrix, times alpha equals y. So given this, we basically have a prediction in terms of just the kernel matrix, and our hyperparameters will give us y. So if we have a new point x in, say, a test set, or to do inference, and we want to try to figure out what the equivalent y should be, well, f of x is, our best setting of the weights, w star transpose times the feature map of x, because we're working in feature space. And then you, again, rewrite w star, which is just big phi transpose times alpha. And this comes down here. And we know what how to transform this function. It's just going to be the sum over all of the data points n. It's the alpha sub I times the kernel of x sub I. This is the data point in our training data, and x, which is the data point we're trying to make an inference on in our evaluation set, in our test set. So, I mean, I'll mention the key result. The key result here is for this regularized problem. It was regularized before. We had like the regular squared loss, and we had the L2 loss, the regularized loss. This solution can be expressed as a linear combination of just kernel evaluations on the training data. And again, this is what I was just going to mention a moment ago. If you're doing a good old-fashioned squared loss with L2 regularization, using a feature map, and the feature map allows you to compute the kernel matrix, which is just the big square matrix of all of the pairwise kernel comparisons between data points in the training data. And the kernel, again, can be linear, RBF, polynomial, whatever you choose, whatever is valid. Every prediction you make is just going to be in terms of the kernel matrix. You didn't have to do any iterative improvements. You didn't have to kind of do gradient descent and find W star. All you have to do is compute the kernel matrix for the pairwise combinations of all your data points, and then you get a model for free. This is very different than the kind of models we've seen before. So like all you have is similarities between existing data points in your training set, and you use those similarities to make predictions on new data you've never seen before. I think that's a very interesting, like, new way of looking at the problem of making predictions. Like, you're making predictions, again, not to emphasize this too much, you're making predictions only based on the pairwise similarity in your training, between points in your training set. But as we just walked through very, very vaguely, that kind of somewhat weird way of doing prediction is equivalent entirely to how we were doing regularized losses earlier with our gradient-based methods for learning, right? So they end up being equivalent to each other, which is, I think, fascinating. So that's kind of the main point over here. So I try to, even though this is under the microscope, I think you might want to try to understand this point about the fact that what we were doing before with regularized L2 losses and what we're doing now with kernel functions are equivalent to one another. And the second point is you can make predictions using only pairwise similarity scores under the kernel of data points in your training set. A little kind of note here, again, we mentioned this previously, but you never need to actually compute the feature map phi x explicitly. All you need to do is just put things through the kernel function. This is not a big deal, really. Like, it's not like you saved a ton of time or anything necessarily, but it's an interesting point nonetheless. Still stretching ourselves a little bit. This is still under the microscope. For a wide class of regularized empirical risk problems of this form, which is essentially the form we saw before, L is just the loss function between the predictions and the predictions f of x sub I and the targets y sub I. And you have this L2 loss, regularized loss in the high dimensional feature space H. Again, this is really a stretch, so I'm going to go over it very quickly. This H is a reproducing kernel Hilbert space, or RKHS. You can read these papers or this book and this website if you're interested in learning more. The minimizer, F star, can be written this way. We saw something very similar a moment ago. This is sum over all your data points of alpha sub I times the kernel matrix of the training data x sub I and whatever argument you're giving it, which could be a data point to do inference on. This is your minimizer. So this is a generalizable. This is generalizable as long as H is a reproducing kernel Hilbert space. And the consequences of this finding is that you can look for solutions in a span of kernels centered at training points and algorithms reduced to solving for coefficients alpha in finite dimensional space. Again, this is a big stretch, but for those of you interested in research and machine learning, please go ahead and feel free to look into this. So here's sort of where things come together, the examples. So we're going to use scikit-learn's 2moons dataset, which I showed you earlier. So this is meant to be non-linearly separable. We're going to make the moons. There's going to be 400 data points. We're going to add some noise, and here's our random state as usual. And then we're going to split the resulting data points in training and testing with a test set size of 30% of the overall data. So here we have 280 points in the train set and 120 points in the test set. Here's a visualization. We've seen it already. So these kind of two C's sort of eating each other. Somewhat yin-yang-ish, but not exactly. So we want to compare two models, a logistic regression. This basically has the linear, something like a linear decision boundary. As we saw before, it's smooth, but the slope of the logistic regression can be arbitrarily sharp, and it still sort of behaves like sort of a grayscale sort of linear boundary. And then we're going to pass the RBF kernel to the SVM with moderate regularization. So SVM is for the topic for another class. The RBF kernel we're going to see later, but just these are both standard sort of off-the-shelf techniques. So here they are. We're going to use pipelines, which we introduced in a previous module. Both of these involve scaling first, using the standard scaler, and then logistic regression and the SVM. Weirdly, in scikit-learn, SVM is called SVC. C, I think, stands for classifier, if I remember correctly, and for the kernel function is just RBF. For now, we're going to pass these two hyperparameters 10 and 1. We'll talk about these a little bit later on. C in particular will come up when we talk about supported vector machines. And that's essentially it. We have these two models. We use these models to fit to the training data, and then we make predictions, and that's essentially it. What are the overall results? Well, you can see how you can scroll down and see how we can copy and run this yourself. But again, I actually recommend that you run everything yourself, just in case there's any kind of mistakes going on here. But you see the training accuracy for the logistic regression is about 86%. The training accuracy for the RBF SVM is about 97%, which is a nice big jump. And more importantly, the test accuracy goes from about 83% to about 97%. Simply by going from logistic regression to an SVM with a radial basis function as a kernel. And here, again, hammering things home, emphasizes why we're doing this in the first case. Here's all the code for you to copy and paste. Nothing much is happening here. We're just plotting the decision boundaries. The logistic regression essentially is drawing out a decision boundary between the two classes it's found. And like I mentioned earlier, there's no line that you can draw through these classes, but this is the best line that separates the purple from the yellow in these 2moons data set. But the support vector machine, which, as we'll see again later, is technically doing a straight line decision boundary through some space, but is drawing that straight line decision boundary through a higher order nonlinear space defined by the radial basis function. And then the result is this nice curved nonlinear decision boundary separating purple from yellow. And there are mistakes, obviously, but generally this is a much better fit than the straight line cut through the space, through the original space. So in logistic regression, the decision boundary is just like a single curve, a straight line after scaling. And this is obviously going to misclassify regions where the moons wrap around each other, like here and here. The RBF SVM uses these kernel evaluations to basically warp the space. So like we saw before, where we move things up into three-dimensional space using simple polynomial transformations, RBF will warp the space non-linearly. In that weird warped space, we can draw these straight lines that will separate our classes. This will capture the curved boundaries and hug the data manifold. Not romantically or anything, it'll just be very close to the separation between the two classes. And the net result of that is you can usually achieve higher test accuracy on this data set and on others too. I'd recommend you go back and, again, play around with things, try to add more or less noise. Like we added a certain amount of noise to the space, see what happens if you just change the noise, for example. Even though you don't know what the hyperparameters mean necessarily, you can change C and gamma to see if you get drastically different results. And you can also pass different kernel functions in. So I passed an RBF as an argument to SVC, the support vector machine, but you can pass different kernel types, like even the linear kernel type, see if you get higher or worse performance with different kernel functions, and C and gamma and so on. We used feature scaling. We used a standard scaler, so this is, again, something you'd be advised to use in many situations, but see what happens if you don't scale with a standard scaler in the pipelines in the code I've provided a moment ago. In this case, you might not see very much of a difference, but it's always good to do the experiment. That's example one. Example two is a digits data set. So we're going to use the digits data set that you're going to see in, or you already have seen, or are seeing in assignment 2. So this should be somewhat familiar to you. We just load the digits data set, we get our inputs, and we get our predictions y, and we split using sklearn's train test split with 25% held out for the test set. And here's just the result. Here's a quick look at some digits. Nothing fancy going here. I'm using imshow to show like two-dimensional images. This is labeled as 0, so you've seen this already, but like the image is X and the label is Y. So this image down here, X, is labeled 7 because this is a handwritten 7. I should mention just for a moment that this simple data set, or data sets like these, basically were the only thing people who are working on machine learning were essentially focusing on for a very long time. When I say only, I'm being facetious, obviously, but just recognizing digits and classifying images into these 10 categories was a big problem for a very long time, but it was the direction that led us to all of the great breakthroughs in neural networks, deep learning, and so on. So once again, I have a RBF support vector machine like before with actually the same hyperparameters. Now we're just going to use a linear kernel instead of using just logistic regression. So we have a linear SVM, we have an RBF SVM, and we make our predictions and see how we do. Here things are a little bit different. So here we get to perfect training accuracy with both linear and RBF SVMs, and we get I guess, slightly better test accuracy using an RBF SVM. I should make a note here that the difference between 98.2% and 96.7% might appear to be small, but these very tiny differences were massively motivating to the original progenitors of modern machine learning when they were working on this sort of data set. So imagine you have a decision context where you want to recognize handwritten digits. You have, you might want to be doing automated form reading, so people are just filling out forms, providing them, they're being scanned, and then we're taking those scans, giving them to AI, machine learning, to transform into actual machine text. This can be run for automatic form reading, postal code recognition, even recognizing, the numbers on buildings. If you're mapping out, if you're doing something like your own street view application. Maybe you're doing pre-processing in larger systems, so maybe just recognizing digits isn't your whole point, but this is part of a larger process of recognizing a wide range of text in much larger systems. Whatever the case, we're using accuracy. So in the previous little table, we're using accuracy, and this is fine when the classes are roughly balanced. So, this is the case usually in these sort of artificial data sets of original just digits by themselves. So you have the same number of zeros as ones, as twos, as threes, and so on. But if you're recognizing house numbers or apartment numbers, numbers on next to doors, you're probably going to see a lot more of some kinds of numbers than others. That's just because of like how streets are arranged. And how you're counting digits. So it might not be a total balance in terms of the digits. In other contexts, you might care about precision and recall. So the difference between ones and sevens, we know from our quote domain knowledge to look somewhat similar, and that, so they know given a confusion matrix that these two numbers might be confused with one another. And it's going to be important for you, maybe for some reason, that misreading a 1 as a 7 might be far worse than reading a 1 as a 2. Maybe 1s and 2s are also confusing, but the difference between a 2 and a 7 is so massive for whatever your use case is. Again, maybe you're measuring medicine, and it might be more dangerous to give someone 7 milligrams of something than 2, right? This is a totally arbitrary case, but I'm just trying to make the point that accuracy isn't always going to be the metric that you want to use. So generally, what you should be doing in cases like these is looking at the entire confusion matrix, and looking at if there's any kind of really strong correspondences between predicted classes and actual classes in terms of mistakes, to see if anything has to be kind of dealt with more specifically. And you can do like F1 scores. Like F1 is a combination of precision and recall that might be more informative than just plain accuracy. If you have time, I mean, this is kind of a bit of a stretch also, but you might want to go back to these exact examples, in particular the digits example, and instead of just rushing straight to accuracy, just looking at the confusion matrix for the models the models and the predictions you've made in this code. There are some trade-offs. So the linear SVM is simple, it's super fast to train, but it might underfit. Again, simple models underfit, or more likely to underfit than large models. The RBF SVM ought to be more flexible, and in practice will often give you higher accuracy, but it can be more sensitive to the hyperparameters and scaling. Again, go back and mess around a little bit with the hyperparameters to see if you can get the linear SVM to have higher accuracy or F1 than the RBF. And it can be less interpretable. This is a bit of a stretch also, but like if a human's going to look at the decision boundaries like we saw between the two moons, it's been suggested in some work, and we might talk about explainable AI later. One of the most baseline methods in explainability tries to essentially draw just linear boundaries between classes at a very local level. It's suggested that human beings, like we understand straight line boundaries, but anything curvy, will deeply confuse our squishy human brains. A few practical considerations. So again, we talked about the standard choices, linear, polynomial, and RBF/Gaussian. In the linear kernel, the formula is pretty straightforward. You're just looking at the product of the two points. This is good when the data is essentially almost linearly separable in the original features, and can be a good baseline, especially for high-dimensional sparse data. The polynomial kernel, here I've changed things a bit because we're going to talk about Ds again soon, but before, anyways, the thing is the same. We do a product between the 2 points, we add some constant term, now I'm calling it beta, and then the order is, I called it P before, and now I'm calling it D again, because previously we called D the hyperparameter in the regression tasks. So we have two hyperparameters, D, the degree, and beta, this constant. This will allow curved decision boundaries, and degree D will control complexity, like we saw before, but this can be sensitive to feature scaling. So again, you can try a standard scaling and without standard scaling. And like we saw with good old regression, D can have a huge effect on your evaluation. And then the RBF kernel, we saw this before, it's somewhat of a simplified version of the actual Gaussian function. It's the exponent of minus gamma to this squared difference. This is very flexible. It can approximate lots of smooth decision boundaries, and usually just throwing in an RBF blindly will get you decent results. It can be sensitive to the hyperparameters. The hyperparameters here, we'll talk about C in a moment with SVMs, but C basically controls the trade-off between, this won't make sense to you now, but when you're going to review these slides for your exams, it'll control the trade-off between the margin size and training errors We'll talk about that in the very next module. We're going to see it. We'll talk about this again later, but small c's give you wider margins or differentiation between the two classes that you have available. This essentially is more regularization, and large c's tries to fit the training data more closely, but this can risk overfitting. And then gamma, small gammas give you smoother, more global decision boundaries, and large gammas will give you very local decisions, very sort of spiky, I guess you can say, very wiggly, I guess you could say. This will memorize training data, or it's more risk, again, of overfitting if you have large gammas. I'm probably not going to ask you to memorize anything about the trade-offs between C and gammas and so on, but in both cases, large values of these hyperparameters gives you more risk of overfitting. Similarly, high degree D in polynomial, like high values of the hyperparameter for polynomials, will also risk overfitting. That's kind of easy thing to try to remember. High values of these particular hyperparameters, high chance of overfitting. And you can choose these through cross-validation like we saw in module 13. Why scaling matters for kernels? Well, so kernels use distances or dot products. Like we talked about this quite a bit, right? So there's these square differences in this 2 norm for RBF. There's the product between these points, x and x prime, in polynomials and in linear functions. So x's again are vectors, right? And every vector represents a different feature, a different dimension. If these individual features had wildly different scales and you're multiplying them with each other, some dimensions are going to dominate the similarity. If you're multiplying very big values with very big values, that's going to give you massive differences, and then relatively massive differences in other dimensions with smaller scales, even if the points are very different in those dimensions. If you're looking at the overall similarity for the overall vector, that's going to not make much of a difference. And therefore optimization can become unstable. Even relatively small differences in dimensions with high variability will be emphasized in kernel functions, and if those dimensions aren't actually informative to the training, but the dimensions with small variability are, then you're going to have trouble learning. Okay, so again, the proof of the pudding is in the eating. So, we're using standard scalar. This is the z-score, the standard scale we saw in a previous module. We just move all the data to have zero mean and unit variance. Some other kind of normalization can happen before kernelization. Making all the dimensions appear more or less the same in terms of their means and variances will give you better performance. Sometimes that better performance is to a very small extent. So here we're doing a little experiment where we're doing an unscaled SVM compared to an SVM using the standard scalar in the pipeline, as you can see here in lines 4 and 5 through 8. And then we just do a fit and we do the accuracy scores. The difference here is not huge. So the unscaled RBF SVM test accuracy is 95.8, and the scaled RBF SVM, everything else being the same, is 96.7. Again, these differences are pretty small. A machine learning person, especially in the 2010s, would see this to be a tremendous gain. Regardless, it is a gain, and like we saw in a previous module, if you're talking about scale, these differences of like 1% can mean hundreds of thousands of customers or patients or dollars, going from one side to the other. So, again, I can't emphasize the importance of standard scaling, both theoretically, because we're just combining vectors together, but also just practically and in terms of implementation, like we saw a moment ago. Again, the proof of the pudding is in the eating, as they say, so do the experiments yourself. Some ethics and risks. So I try not to repeat myself too much. Some of the ethics and risks will be common across modules, but I just want to mention some of them are also unique. So these complex boundaries, we've gone from very simple boundaries between classes, and now we have more complicated nonlinear boundaries between categories. We saw kind of a cartoon example of the 2 moons. But if you have more complicated boundaries, this can make it somewhat more difficult to audit who is being misclassified and why. When I say who, I mean groups of who. If there's any kind of systematic bias against a demographic group, if you have like very complicated decision boundaries that really map out individuals, then this can be too complicated for us to kind of visualize that there's a difference between demographic group A and demographic group B. So fairness and bias reduction can be more challenging, at least in theory. Kernel functions rely on pairwise similarities, so we're comparing two data points to each other. And this is beyond it. I might try to, like, if someone asks me and reminds me on the forum, I can add a citation here. But there's lots of ways that a nefarious hacker can use information that's stored somewhere to extract information, and even the kernel matrices, where we just kind of combine all of the data points together in terms of their similarities, that can sometimes expose information that can be helped. That can help a hacker recover information about the individuals in the data. So you might be able to infer sensitive patterns just by using the kernel, the pairwise similarities from before. So privacy is a bit of a concern here if you're not careful. Again, this is a subject for even other courses in responsible AI, but we'll keep on coming back to it. There are mitigations. Again, repeating ourselves, try to inspect performance across relevant subgroups whenever you can, and document kernel choices, like document everything, make sure you're using model cards, and so on. So kernels are used beyond SVMs. They show up all over machine learning. Here's a lot of papers for you to check out if you're interested. This is only curiosity again, so I'm not going to ask you questions about these. And some of these also refer to topics later on in the course, like principal component analysis. But the ideas of kernels, the ideas of simply using nonlinear functions to compare two data points together, and then using combination of all of these comparisons in a kernel matrix, come up in kernel ridge regression and Gaussian processes, principal components analysis, and like reducing feature spaces, strings and graph kernels, neural tangent kernels. These aren't the most popular models, but this is published in Europe's several years ago. So they keep on coming up, even in relatively recent literature. Thinking in kernels, this is part of a broader representation mindset. Again, just because kernels aren't necessarily, top of mind or front and center in massive transformer neural networks, doesn't mean they're not useful. Learning about this stuff is going to always be helpful. Having a varied toolkit that you're familiar with is far better for you than just having a single hammer, so to speak. Please go ahead and do these quick checks. I think I made, like, the LaTeX is not compiling here, so I'm going to make sure that the LaTeX compiles before I upload this module. Here are the references. As usual, thanks so much, and see you in the next module.